So where we ended up on Tuesday was reduction aldehydes, ketones, and esters, and then reactions of those with Grignards. There's one other reduction we need to look at, which is catalytic reduction of carbonyls or ketones and aldehydes. So the most common reduction is going to be the hydride reduction, either sodium borohydride with aldehyde and ketones, or lithium hydride for carboxylic acid derivatives. But we can also do this with hydrogen and nickel. Platinum and palladium work, but nickel is one of the more reactive of those three metals. But usually this takes high pressure, right, and a decent temperature. 1,000 psi sounds like a lot, but a oxygen tank is 2,000 psi. Acetylene tank maybe 2,700 psi. So these are things you can do within a normal what we call, unfortunately, a bomb reactor. What it is just something that can get the high temperature and high pressure. So it doesn't actually explode, but it does allow you to get the high pressure. Because of that, most times in the lab, you're just going to use sodium borohydride. There may be reasons to use the catalytic hydrogenation, but it does take a little bit more oomph to get the reaction go than you do with hydrogen and palladium on just an alkane. The process would be syn. So if we think about this is a metal type catalyst, so our hydrogen is absorbed to the surface, our carbonyl species would be absorbed to the surface, and that means that when it works, our two hydrogens are actually going to be adding from the same side, right? So this would be a syn type of addition. So all our metal catalysts, except for the dissolving metal, which is a dissolved metal, but our metal substrate catalysts, such as reduction of alkene to alkanes and alkynes to alkenes, they all are going to give us a syn addition. Same thing here. We would give a syn addition. And so that's most of the reactions forming alcohols. So let's look at reactions of alcohols. And since we just looked at reductions, let's look at oxidations. When we look at the oxidation of alcohols, it's important to think about, primary, secondary, and tertiary. When we look at primary, we can go to the aldehyde, right, would be the first oxidation step. But we could also potentially take that without breaking a carbon-carbon bond, go to the carboxylic acid. When we look at a secondary, we could take a secondary alcohol, and we'll just put a generic oxidation process here. To go to the ketone. But any further oxidation of that, okay, is going to be more difficult. Okay. There's one specific reaction you'll see next semester called the Baeyer-Villiger oxidation, but that's a very specific reaction and does not get you a carboxylic acid. It actually gets you to an ester. Okay? But if we think about just standard oxidation process, and the reason I say it's a special is it is an oxidation, but because it's doing an insertion, not because it is abstracting a proton to get us to a higher oxidation level. If we look at the tertiary, we get no reaction. And the reason for that is most of our oxidations are going to be the loss of really two hydrogens, those two hydrogens. And if we think about this is not a beta, but this is an alpha hydrogen, right? Exactly where it's attached. And we have that in this case, right? So you can think about it, we had two oxygens, one's being removed, one is staying to give us the aldehyde. In the ketone, again, we have one hydrogen there that we're going to be removing. And we have one there. By removing both of those, right, that's how we get the oxidation. And we'll look a little bit on the mechanism here. But then when we look at a tertiary alcohol, we have no alpha hydrogens, right? So we have no alpha hydrogens to remove. If we were going to oxidize this, we'd have to break a carbon-carbon bond, right? That's going to be a high energy reaction. And by the time we've done that, we've probably destroyed the molecule per se. Okay. So how do we do these oxidations? Okay, there's a couple of ways to do these. The one that's most common that you're going to see is going to be a chromic acid oxidation. The problem with chromic acid is that it's not stable. Right? So therefore, we need something that is stable, that can make chromic acid in situ. So what we're going to be looking at is two sets of reagent. One is going to be potassium dichromate. In aqueous acid, or we're going to be looking at chromium trioxide in acid. So these are both reagents that give us chromic acid in situ. Okay, so we can't take chromic acid in a bottle and add it to a reagent, but we can take the sodium or potassium dichromate in acid and water, or we can take the chromium trioxide in acid and water. If I use either of these and do not show the other one, I apologize. Both of them are interchangeable. Okay? So the product you get from either of these will be the same product. So the reagents, sometimes as I've gone through this in the past, I've only shown one in one of the processes, and the students get confused and think that the CrO3 only gives X, where the potassium gives Y. That's not the case. These are interchangeable. They both in situ create the same thing, which is this chromic acid. So if we look at the primary alcohol with chromic acid reagents, right? So the CR, the potassium dichromate. Oops, that's supposed to be a 2 there. Please correct that. That's a 2. O7, sulfuric acid. Aqueous. If I have a primary alcohol, I'm going to end up with a carboxylic acid. So if we look up here, when we looked at primary alcohols, what chromic acid is going to do is do both of those oxidation steps, right? It's going to oxidize up to the aldehyde, and then it's going to oxidize up to the acid. So in one step, couple of steps mechanism, but one reaction, we're going to end up with the carboxylic acid. If we try and we take the same thing with the secondary alcohol, we'll end up with a ketone. This isn't because the chromium acid is not strong enough to oxidize it further, it's that it won't oxidize further, right? So the ketone is going to be the terminal oxidation for this process. Where in the primary alcohol, the terminal oxidation was not the aldehyde, but the carboxylic acid. So for a mechanism, we get attack of the alcohol onto the chromium. Then the water can come in, extract that alpha hydrogen. We get the reduction of the chromium. Then we get a proton transfer. And then in this case, right, this can proceed again, and we won't go through the mechanism here, but this can proceed again with the chromic acid. Right, to give me the carboxylic acid. Similar process. The carbonyl attacks the chromium, making that complex, but then instead of then the water attacks the carbonyl, slightly different, and a little bit, it's not too complex, but the first step is the one I want you to focus on. It turns out that what is allowing this to continue is the water. So water is an integral part of this mechanism, right? And the water is going to be what's going to attack. So this hydrogen, oxygen here is coming from the water. So what they discovered is if you can eliminate the water from the process, you can stop at the aldehyde. that the water is essential to get us to the carboxylic acid. So that created the next one, which was oxidation with PCC. And PCC was pyridinium chlorochromate. For this one, we can use this PCC reagent in a solvent that we can keep dry. Right? So something like methylene chloride, if they don't show methylene chloride, that's okay. But the reason it's showing methylene chloride is not that it's part of the reaction, but that it signifies a dry solvent. A dry solvent means without water. And that can stop at the aldehyde. Now, the first step of PCC oxidation is very similar to that of the chromic acid. So therefore, we can also take secondary alcohols with PCC and end up with ketones. Questions about the So if we look at chromic acid, and again, there's two types of reagents, the dichromate or the chromium trioxide, right? Either of those two will react with primary and secondary alcohols. With primary alcohols, it goes all the way to carboxylic acids. For secondary alcohols, it stops at the ketone. The mechanism is reaction with the chromium, deprotonation of the alpha hydrogen, and then reduction of the chromium to give us our main reaction, transfer reagent, we get the aldehyde, but in water, it'll go all the way to the carboxylic acid. So to stop it at the aldehyde, what we do is use pyridinium chlorochromate, which will give us all the reagents we need for the reaction, but without water, right? That's what this signifies, is the dry reagent. And so primary alcohols go to the aldehyde, secondary alcohols will go to the ketone. Now, since the secondary alcohols go to the ketone, you'll see that synthetically, the pyridinium chlorochromate is not a bad reagent to work with, a little bit easier than the chromiums. And although it costs a little more in a synthesis lab, you'll see PCC used to turn secondary alcohols into ketones pretty commonly. Okay. Any questions about these? So,
sorry to interrupt, sir, but somebody in the chat had a question.
Sure, let me look at it. Okay. Because the lone pair is reacting. Are you talking about this? I see they're asking, why is there a double bond on the first step? Oh, I see what you're talking about, the oxygen. Sorry. That is correct. That should be like that. Okay. Was that the question? You can just,
Yes, thank you.
okay, yeah, sorry for that mistake. Okay. Okay. All right, so now let's look at conversions of alcohols to halides. Okay, conversions of alcohols to alkyl halides. We've seen some of these, right? We can take alcohols, react them with acids, right? And we can get the chloride. The process is going to be most likely SN1-like. So you convert the good leaving group. And then depending on what's going on, you're either going to get the chlorine to come inside and attack. So here, this is secondary. So this is possible. But potentially we could have also formed the carbocation, right? If this had been a tertiary group. And this can give us rearrangements. The HCl also may be giving us possibilities where we have some complications. So let's say that we wanted to convert this alcohol to this chloride without moving a double bond, right? If we just use the simple HCl, we're going to not end up with this product. We're going to end up with these two products. So although the HCl works, hydrobromic, hydrochloric acid works to convert alcohols to ketones, to alkyl halides, there are potential complications. I could go through a rearrangement, right? I could get secondary reactions. There's another functional group there. We could be more systematic about the conversion. At the first step, we could convert that with something like tosyl chloride. Remember, activation of alcohol to the tosylate. And then we could do an SN2 type reaction. To get the chloride or anything. Once we make the tosylate, we've got lots of different options. Okay, this is a two reaction process. Okay. So if we look at it, we have a few ways now already. So here's one, right? This one we've already seen. Two. We'll introduce a couple of new ones today. We can do this with SOCl2. The way to think about the SOCl2 is that we're going to be activating the alcohol and doing the chloride substitution at the same in the same process. So the first step mimics the tosylate somewhat. The lone pair on the oxygen reacts with the the sulfur. So we have oxygen attacking the sulfur. And at this intermediate, the oxygen comes down, kicks off one of the chlorines. Remember the pKa differences between HCl and H3O plus. The chlorine is actually a better leaving group than the than water, H2. Remember that pyridine can be a electron sink. So the pyridine is important in this process. I'll pull this proton. And then the chlorine comes in, attacks this position, kicks the electrons around towards the sulfur, and actually kicks off the chlorine. And to show our stereochemistry, I'll show that down. So this would be backside attack. All right, so if we have stereochemistry, we're going to get inversion. It's going to give us the sulfur dioxide plus the chlorine, which goes off with the pyridinium. So the nice thing about this reaction is that we end up with the chloride in a pretty straightforward one-step reaction. SO2 is a gas, so it'll bubble off. The pyridinium chloride is a salt. So if I do this in an anhydrous, less polar reagent, such as methylene chloride or maybe hexane, the salt will actually precipitate out of the reaction. So I can do this reaction and end up with my product and solvent and just have to remove the solvent. So there are no byproducts that I have to really worry about. I just have to filter it. So this is a pretty straightforward synthesis. So SOCl2. Now the SOCl2 works, but the SOBr2 is a little bit too unstable to be an effective reagent. So when we look at bromination, and again, here's our third method. When we look at bromination, we need to use a different reagent. Similar process, it both activates and adds the bromide in the same process. But instead of using SOCl2 or SOBr2, which is not stable, we're going to use PBr3. First step, we get attack at the phosphorus, lose one of the bromines. And the bromine can come in and attack, again, nucleophilic substitution type anti. So it's going to attack the antibonding orbital, kicking off the phosphorus. This results in my bromide plus then the phosphorus. One of the driving forces for this reaction is the strength of the phosphorus oxygen bond. Okay. Questions about these? Another review of reactions we already know, the conversion of alcohols to alkenes. Remember, we can do dehydration of an alcohol to give us the alkene. This is an E1 style process from the end of elimination project, right? So this is dehydration. And since it's been a few weeks, go through the mechanisms. So we protonate. Then we get formation of the carbocation. Now we could show the sulfonate anion here, but again, the water is the better base in this case. So we'll show the water since we just created it. We pull off a beta hydrogen. Giving us the double bond. Can you think of any other ways to do alcohol to alkene conversions? So this is an E1 type process. We could also, like we did with our other, with our alkyl halide, is turn this into tosyl chloride, tosylate, right, with the tosyl chloride. So make that a good leaving group, right, and then add a good base. Let's see, a good non-nucleophilic base. Well, we can use the potassium base to give us a double bond, right? Difference here is that this mechanism would be more E2-like, or E2, not like, it is an E2, versus the first one when that's going to be an E1. So this is one of the things that's happening now and will continue to happen throughout the year, is that whenever you come to another set of reactions, you're going to see reactions you've done before. So one of the things that I said is you're not going to get questions over again, but they're going to build on each other. So if you don't know stereochemistry, you're not going to be able to do stereoselectivity when we get the reactions, right? But I won't go back and ask you a question. This is one of those cases where, yeah, you're going to see those again. But I'm trying to reintroduce those in a slightly different format, right? So the eliminations were just focusing on eliminations. Here, the eliminations are focusing on the alcohol becoming the alkene, right? So we're doing a specific conversion with that elimination and showing some very specific reagents that can give us that product. So this will help as you start to build these up. Although we've shown a lot of reactions with alcohols. If you notice, the sodium borohydride, lithium aluminum hydride were new reactions. But today, the oxidations were new reactions. So there's a couple of new reactions there. The PCC was new, but this conversion of alcohols is an old reaction. This conversion of alcohols is an old reaction. This one's new, and old, right? So we're showing a lot of reactions, but as we continue through the book and as you get into next semester, you're going to start to see deja vu more and more, and that should help you dissect those. So one of the things that's helpful is to go through and say new and old, and that way you can focus a little bit more on the new and just review the old. Questions about that? Okay, let's move into ethers. A couple of the first synthesis of ethers are actually just versions of synthesis of alcohol reactions. If I take a alkene and react it with water and acid, I'm going to end up with the alcohol. Oops. But I can do the same process, change the water for a alcohol. Okay, and Me is CH3. Okay. So if you saw ET, that would be ethanol. Right? So some abbreviations. They'll let the Me throw you off. It's just methanol. And why did they use it? Because it used to be hard to do subscripts. So they started using Me, ET, so forth. So the process here is similar, right? We're going to first protonate our alcohol. So our reagent is actually the protonated alcohol, just like it would be the hydronium. So the nucleophile, which is the alkene, reacts with that, gives us the, oops, and I probably should, so that it looks like the products, we'll put the H here. We get the carbocation. Then my alcohol attacks instead of water. And then we get a proton transfer to get to final product. Right? So this is hydration of an alkene, but instead of using water, we're using an alcohol. Same reaction we saw earlier. Right? So we see the ether formation, if we want to look at it that way, versus the versus the alcohol. Okay, so this is just an old version. I think some of your practice problems actually had this in there, just trying to highlight it. Oh, I started at the bottom. Yes, thank you. Similarly, another one we could be looking at is the oxymercuration demercuration. Remember that in the first step, it's the water that comes in and ring opens that mercury. So if I do this in a different solvent, I could form the ether versus the alcohol. And again, just a version of an old reaction. We're just changing our solvent and we've changed the product. Okay, questions about these two? The main way to make ethers is the Williamson ether synthesis. And I'm going to tell you the same thing that I've told many groups of students before. If you were going to make an ether, and the main way to make ethers has ether synthesis in the name, you should try and remember that. For some reason, Williamson ether synthesis always gives students a hard time. I'm not sure exactly why. Williamson ether synthesis, you're making an ether. I'd go with the ether synthesis as my first process. It might be that it looks like some old reactions, and it is like some old reactions, but try not to get caught up by this one. This is one of those where some of the other reactions, if you forget that primary alcohol goes all the way to carboxylic acid with a chromic acid, that's understandable. But just to totally miss the Williamson ether synthesis as the reagent process, you know, I'm telling you this, hopefully that it'll help decrease. This is one of those always that makes me scratch my head when students miss these problems. The Williamson ether synthesis, and this may be the reason, is that it looks a lot like something we've already seen before, was we first going to make the alkoxide, and then we're going to have that alkoxide react with some type of electrophilic carbon. Okay. So more or less, it's making the alkoxide and then doing an SN2 reaction. Making the alkoxide, what we do here is there's a couple of reagents that make it a little bit better, but anything that can make the alkoxide will work, right? So most bases. And then here, all I need is an electrophilic carbon, unhindered preferred. Right? So unhindered preferred, because this is going to be an SN2 type process. So if we look at the mechanism here, the reason that sodium hydride is a useful one is that it's going to give me what we call quantitative alkoxide formation. And there's two reasons for that. One is the pKa of hydrogen, right? So the pKa of hydrogen is very high. It's very unstable as the negative. So the hydride has a very high base. And so I've got a big differential between my pKa's. One's in around 50. The other one is around 16. The other is what happens with the hydrogen once this reaction occurs. Hydrogen is a gas, right? So it's going to bubble off. And so as a gas, it goes away. If it goes away, can the reaction reverse? No. So we've got a huge pKa difference here, and the hydrogen can float off. Okay? So that's not the only base. Don't let that throw you off if they add something else. But the reason you'll see sodium hydride quite often here is that it's not that hard to work with, and it has a lot of advantages to form quantitative Okay. Since I brought that up, let's look at non-quantitative. It's not qualitative, but non-quantitative. If I took something like this and I added sodium hydroxide, that would form the alkoxide, right? But due to the pKa difference, this would be in equilibrium. So for the Williamson ether synthesis, we don't want an equilibrium type deprotonation to form the alkoxide. We want a quantitative. There are processes, and we'll look at some later, where you will see some next semester, where the equilibrium process is favored over the quantitative. So you'd want to use a base that was just slightly more basic to do the deprotonation. But in Williamson ether synthesis, we want a quantitative epoxide formation. So once we form that epoxide, the alkoxide, then that reacts with our electrophilic group. In an SN2 type process. To give us our ether. So it's just alkoxide formation followed by electrophile. The first is an acid-base reaction, and this is my hypothesis on why students almost every year have a little bit of difficulty, is that the first step is just an acid-base reaction. The second step is an SN2 reaction. So instead of seeing it as the Williamson ether synthesis as a package, you see it as an acid-base and an SN2, which is mechanistically correct, but it also then makes you forget how to make an ether when you're in the middle of an anxiety-driven process, which anxiety-driven process is educationese for exam, right? So acid-base transfer, proton transfer, and then SN2. Retrosynthesis, if we had been trying to make this one, right, we've actually got two ways to think about this. So with the Williamson ether synthesis, right, I've got two bonds to oxygen. So that means I could have started with the alcohol and the electrophilic carbon, or I could have started with the electrophilic carbon and the alcohol. Okay, so to get to this product, right? I've got two possible ways to do it. You know, I could think about making this bond, right? Or I could think about making that bond. So one of the things you're going to need to do when you're looking at Williams-Ether synthesis is decide on which one of these is preferable. In this case, both of these would probably work. But which one is preferable has to do with that second step. The first step, making the alkoxide, that's an acid-base reaction. Is there going to be any substantial difference? No, there's going to be very subtle pKa differences between our alcohols. So if we're using a strong base like sodium amide or sodium hydride, it's going to pull the proton, no problem. The difference is going to be in the second step, and the second step is SN2, right? So therefore, it's the second step we need to look at. And therefore, we're comparing, right, this group to this group. And why both of these would work in this case is these are both decent SN2 processes, right? This is a methyl, this is a primary, right? So by SN2, both of these are possible. Which one is preferred? Which one is less sterically hindered? The methyl or the primary? Well, the methyl only has hydrogens, right? The primary, although still not very sterically hindered, at least has one carbon, right? So when we look at these, the methyl, right, is going to be less sterically hindered. So it is the preferred substrate. Okay. So I would put process 1, the one that we've shown, as being preferred over 2. Okay. Let's do another one of these. I'll give you some time to think about it. Think about the two possible pathways. Okay. So that's my ether. Think about the two possible pathways. So show the alcohol and the electrophile substrate, and then show the other alcohol and the electrophilic substrate. You've got two oxygen carbon bonds you could make. Okay, let's take a look. So if we are breaking the bond between this carbon here and that oxygen, right? That means that this is going to be our substrate. So I can add, you know, some type of good leaving group on there. Halides are usually the thing that's shown. Plus then I'll have the oxygen attached to the other side, which is this tertiary carbon. Then if we look at the break 2, that means that this is the alcohol, right? And this is my substrate. So comparing these two, that means we're going to be comparing this bromide or this bromide. This is primary, this is tertiary. If we're thinking about SN2, is the primary good? Yeah, primary will work. How about the tertiary? No, right? So tertiary is not going to work. So in this process, there's an obvious. The obvious is going to be this side. That means that I'm going to start with this alcohol, right? Use some kind of strong base, sodium hydride, sodium amide, something that'll give me a quantitative base. The only thing I don't want to use is something like sodium hydroxide, because that'll be a equilibrium type base. And then we'll have that react with this substrate. Okay. Is there a competition here for this specific one that I need to be worried about? Could I also get elimination with this tert-butyl group? Yeah, in this one you could, right? Because this is a pretty good E2 style, E2 base, right? So I would expect some of the elimination product, right? But if we were going to make this ether, this is the best way to make ether. If I wanted to favor SN2 over E2, there's some things I can do as far as my solvent choice. I can change my temperature. I can do a lower temperature. I could also do concentration differences to drive SN2. Okay. This is not always going to be the case. A primary or secondary alkoxide is not going to favor E2 over SN2, but in this specific case, you would. But in this specific case, making these two, there's only one of these two paths that'll work. The second path here won't give me the product, right? So I have to use the first path. The first path is not a clean reaction, but it's at least a decent reaction. Okay, questions about these? Okay, before we do some practice, one more thing we need to look at, and that is intramolecular. Actually, two more things we'll look at. It looks like we have plenty of time. Okay, so intramolecular Williamson ether synthesis. If we react this alcohol and it has a good leaving group, in this case, the the bromide, again, we use some type of good base. In this case, we want a base that won't react with our bromide readily. Okay, so we get a proton transfer to form the alkoxide. We get backside attack. So we would want this in a low concentration. And that will form, we number these out. This is always a good idea. So we go 1, 2, 3, 4, 5, 6. So we have 1, 2, 3, 4, 5, 6. So the intermolecular works pretty well for 6-membered rings, 7-membered rings, 5-membered rings. 4-membered rings don't work too much because of the stress in there. And it turns out 8-membered rings, okay, 9, a little bit difficult, right? Because it's just having a hard time finding itself. Now, it does turn out that 3-membered rings do work, but only if they're set up just right. So let's say that we took this alkene and we did the hydrohalogen halohydrin reaction. Sorry, halohydrin reaction. Okay. And so we got our bromine and we've got our alcohol. Then if I took and I added a good quantitative base, what I'll end up with is the epoxide. Now the epoxide is a specific type of ether, but if we look at it, it's an oxygen between 2 carbons, right? Epoxides are specifically 3-membered rings, but this is in the area of an intramolecular Williamson ether synthesis. The way this is working is that I have my intermediate set up to do a backside attack. Right, so that deprotonates here, oxygen goes there. Okay, and then this is set up right in the right geometry to do a backside attack to give us this intramolecular epoxide formation, right? It is a form of an ether. It's a cyclic ether. Questions about this one? We'll go over this again on Tuesday because we'll look at formations of ethers, and you have 2 forms of ethers, this one and the one we saw with alkenes. Reactions of ethers. It turns out that ethers are relatively stable. They make good solvents. They don't react with a lot of stuff. If we look at it, they're not great leaving groups, right? We'd have to protonate it to get it to leave. They have lone pairs, but because they have 2 carbon groups, they're not great nucleophiles. They can coordinate metals, so that makes them good. So THF is a good solvent. This is THF. It's just a cyclic ether, right? But it's unreactive. It makes a good solvent. It's the solvent that we use for the borane. It's a good solvent for, this is diethyl ether. Because they are somewhat polar, right? They're pretty polar. They're not as polar as a protic solvent, but they're not very reactive. So they make really good solvents. The only problem with ethers is that ethers, because of the oxygen, can oxidize to make peroxides. And then the peroxides can be somewhat dangerous. So ether is highly flammable. And if you let ether sit in a bottle too long, the oxygen will start to react with the ether and form crystalline peroxides. So you have this process, right? So you end up with these, right? And this becomes crystalline. And so if you ever see a bottle of ether and it has any crystals on the mouth of the bottle, do not touch it. Do not open it. Don't tell somebody about it, right? It needs to be disposed of properly. Because what happens is when you get these crystals formed on there, if you open it, you're going to cause friction to those crystals. That'll cause those frictions to destabilize, which causes them to spark. And diethyl ether is highly flammable. The highly flammable ether then catches on fire, which causes an explosion. So old ether bottles with these crystallines can explode, not because but it's a chain reaction. The epoxide makes a spark, the vapor from the ether catches on fire, and then the bottle goes boom. So ethers, except for the oxidation process, are pretty stable. The one thing that can happen is I can cleave these with acid, right? So the acid would make a good leaving group, and I can end up, and if I use two equivalents, I can end up with two of the bromines, right? The way this would work, so I can do acid cleavage. So lone pair reacts with the hydrogen. I get a good leaving group now. I've got my bromine. Bromine can come in, attack here. That then results in, and so that it looks right, let's put the bromine down, plus then the alcohol. If I have another equivalent of this, right, so two equivalents or an excess, this reacts again. And then again, my halide comes in, attacks that, and I get another equivalent of the bromine. Okay, so with excess or two equivalents, I'm gonna end up with two alkyl halides, right? Because I can cleave the ether and then I can get a substitution, the alkyl halide. And again, if we think about it, this last step is a conversion of alcohol to a halide. If we only have one equivalent, right, then we have to look and see what's going on. And it depends on whether the reaction could potentially go through SN2 or SN1. I mean, sorry, E1, yeah, SN1 or SN2. Yeah, sorry. In the first step, we have the possibility of an E1. And anytime we have a possible E1, and it turns out in this case, because of the HBr, the conditions, that's the driving force. So if we think about it, we protonated this and we have this tertiary group. Because we have the tertiary group, we can get the, I'm sorry, we can get not E2, I keep getting those messed up, SN1 type process. And we get the alcohol plus then we get the carbocation. and then the carbocation reacts with the bromine. So what you have to ask in this case is, when I cleave this with one equivalent, do I have the possibility of a stable carbocation for an SN1 type process? If so, that stable carbocation is going to add to the bromine. In the second step, I do not have either side, right? This is primary, this is methyl. Neither of these sides will make a stable carbocation. So therefore, this is going to go through an SN2 process. As an SN2 process, and again, I'll just eliminate the first step, which is the protonation step. Now the question is, which of these two sides is going to be faster to react with the new nucleophile? And in this case, we have a methyl and a primary, so it is the methyl that is more reactive, all right? Which then gives this side as the alcohol plus the methyl bromide. Okay. So when we're looking at one equivalent, we have to decide whether it's an SN1 process or an SN2 process. If it's an SN1 process, the one that would make the most stable carbocation is going to end up with alkyl halide. If it can only go through an SN2 process, then the one that would go react faster in an SN2 process will be my alkyl halide. Okay, and that gets us